So let's do this one. This is a fun one. A drop of water weighing 0.48 grams condenses on the surface of a 55-gram block of aluminum that is initially at 25 degrees Celsius. If the heat released during condensation goes only toward heating the metal, what is the final temperature in Celsius of the metal block? The specific heat capacity of aluminum is 0.903 joules per gram degree Celsius. My understanding is that they call these word problems now. When I was a kid, they were called story problems. And this isn't a very interesting story, but it is kind of a story, isn't it? It just goes on and on. Do not panic when you read a question like this. You just need to look at it, pull pieces apart, and make sense of it. Sometimes it helps to draw a picture. So I'm going to draw some pictures. So they're talking about a water drop, right? So here's my water drop. This is kind of a funny looking water drop, but that's okay. What do I know about it? It has a mass of 0.48 grams. That's condensing. So that means it was in the gas state and it condensed on the metal, right? So I got my double gulp right here of Diet Dr. Pepper. I don't know if you can see, there's water condensed on the outside. Where did that come from? Is the cup leaking? No. There were ice cubes in here and it's cold. And so water from the air is condensing on the outside of the cup. So that's what we're talking about here. This water is condensing. It's making a drop that weighs 0.48 grams on this aluminum. There's energy involved in condensation. That's the heat of vaporization, because condensation is the opposite of vaporization. So when we have condensation of water, the heat of vaporization of water was 40.7 kilojoules per mole. We learned that 2 slides ago. So that's a piece of information. It wasn't given in the problem. You don't have to memorize that number. If you need it on a test, I'll give it to you. So it's condensing on the surface of a block of aluminum. Okay, so aluminum is kind of silvery colored. So here's our block of aluminum. I'll call him Al. What do we know about the block of aluminum? It weighs 55 grams. And it started out at a temperature of 55 degrees Celsius. I'm sorry, 25. I don't know where 55 came from. Oh, it's the mass. 55 grams. And its initial temperature was 25 degrees Celsius. What else are they telling us in this problem? The specific heat capacity. Do you remember the letter that we used for that? There's that Q equals MCAT. This is the C. So C for water is 0.903 joules per gram degrees Celsius. So now we have to think about what's happening here. It says, assume that the heat released, pointer, come on, there it is. Heat released during condensation goes only toward heating the metal. What's the final temperature? So we're trying to find the final temperature. As the water condenses, it gives off energy. And they're saying that all of that energy is going to go towards heating the aluminum block. Well, we had an equation for that, didn't we? Q equals mc delta T. So we know what the m is. We know what the c is. Delta T is related to what we're trying to find. How are we going to figure out how much heat there was? Well, we've got the mass of this drop of water, and we know how much heat it releases per mole as it condenses. So we're going to take 0.48 grams of water and figure out how many joules of heat. So I don't have enough room. So I make room. Let's do that more efficiently. You shouldn't be able to go off the slide, but you can. Pardon me? Maybe I could, I don't know. I'm having issues with aspect ratio and YouTube these days. Okay, I got sidetracked. Yeah, we're trying to figure out how much energy is released by that water droplet. So we've got 0.48 grams of water, and I'm going to choose joules as a unit because when I plug something into this equation, this has joules. Otherwise, I might choose kilojoules, but I'm going to use joules. So I've got this guy. This is kilojoules per mole. So if I converted grams to moles, I could use that to convert to kilojoules. So sad J. And then convert to joules. .48 grams, moles on top, grams on bottom. Kilojoules on top, moles on bottom. Joules on top, kilojoules on bottom. Well, here's our relationship between kilojoules and moles. 40.7. So 40.7 goes in here. Kilojoules and joules. That's like the kilogram-gram conversion we did. Kilo means 10 to the 3. So I put 10 to the 3 where the kilo is not. I'm not going to say 10 to the 3rd. Kilojoules is 1 joule. That's like saying 5,280 miles equals 1 foot. Is that correct? No. So there's that. And then for this, we need the molar mass of water. We just did that, 18.016. 0.48 divided by 18.016 times 40.7 times 1 EE3. And this gives me 1084. How many sig figs, if I was going to stop here, how many sig figs would this number have? 2. Because of this one. I want to keep 2 extras. So this number has 2 sig figs, but I'm going to keep the 8 and the 4 to avoid rounding errors. Calculator says 1084.36 blah, blah, blah. So that's joules. This is the amount of heat that was released by that water condensing. This is the amount of heat that goes into heating up the block. So this is equal to Q in our equation down there. I want to know what the final temperature is. If I calculate the change in temperature, then finding the final temperature would be relatively straightforward. So I want to rearrange this equation and get delta T by itself. So I'll divide by M and C. So M and C cancel out here. So delta T equals Q over MC. So we just figured out what Q was, 1084 joules. Down here we've got the mass of the aluminum block, 55 grams. And we've got the specific heat capacity, 0.903 joules per gram. Yeah, that's a gram, degrees Celsius. The joules are going to cancel, the grams are going to cancel. I'm going to end up with degrees Celsius as my unit. 1084 divided by 55 divided by 0.903. 21.83. This should also have 2 sig figs. I'm just going to keep those 2 extras. That's the change in temperature. Did the block of metal get warmer or colder? Warmer. It's going towards heating the metal, right? So if this is the change, and that's the initial temperature, it must be 25 plus the 21.83. So T final equals the initial plus the change. So that's what, 47 degrees Celsius. Any questions? That's a challenging problem for 3A students. I wouldn't give you that as an exam problem. I think it's great to put stuff like that on worksheets, though, because it makes you think, makes you ask questions. Personally, I find problems like this fun. You know, it's a puzzle. We got to figure it out. What can we do here? What can we do there? How we can pull things together.